All right, welcome everybody. This is the storage and I/O session for CHPC for this year. We have 3 research talks and a vendor talk, or 2. Can't remember exactly, but we're going to do them going through. Originally, we had a different presentation for the first one. Unfortunately, they had a personal emergency and had to cancel, so I'm going to fill in and do my best to still keep things relatively on topic here. This is just a regular storage and I/O session here. So we'll give everybody else here another. No, I think we'll just go ahead and go because we've been going for about 10 minutes now, and this way we'll be a little bit closer to what's supposed to be on time. So with that, we wanted to present here. This is a project that Scott Paskey and I and some other people have going on right now. This project is focused on the sound bad. Sound is bad?
I mean, I hear you,
Is that any better? Yes? Okay, all right. So this project is looking at how do we get more advanced kind of queries looking at derived quantities on scientific data rather than just searching through raw data. So what I'm going to present here is kind of looking at the development that we've had over time and then how each one of them has advanced what we've been able to do against the observational and simulation data, and at the same time, what kinds of new opportunities it enabled for us in terms of being able to learn things from our simulations and our observations. So the kinds of applications that we really want to look at, this is just a list of several of them. I won't go into a lot of them. I know the computational fluid dynamics is a common one that South Africa uses as well as basically everybody else in the world. For these kinds of applications, what we want to be able to do is to, instead of just saying, I want to look at all these little data points, I want to be able to go and look at what kinds of things are actually interesting about the data. So combustion is a good example because you don't actually want to look at any of the individual quantities necessarily in combustion. You want to look at a combination of them that, for example, can say that combustion has started. And that will end up being looking at how several of them interact together, and then the combination of them represents the fact that combustion has started. So that's the kind of thing that we want to be able to represent here. And this is just an example of some of the other kinds of things that we want to be able to support as well. So the basics of dealing with this raw data, as I think everybody here knows, is that you have to be able to move that data from the computational area into storage, and then later when you're doing analysis, you want to move it back. And the problem is that the disk controller is really your performance limiter. And because of that, you want to minimize the number of times and the amount of data you have to traverse across that disk controller. So these kinds of solutions are really focused around giving you ways to be able to find what you want in the data without having to read the whole thing again and again and again over time. And global indexing is one approach that we use. Feature indexing and tagging. So for example, on like a weather simulation, being able to tag an area of a time step and say there's a storm in this location. That way we can then go back and find that directly without having to load that entire area and then search through for the factors that would identify a storm. Basic query support could be something like just looking for when the minimum or maximum value for a particular variable exceeds or a particular threshold. And that way you can then find something like when the temperature reaches a particular level. And those kinds of things are also useful, but they're relatively basic. What we really want to focus on longer term is how do we do more advanced kinds of queries, looking at these combinations of things, such as like when does the combustion start. The existing kinds of libraries don't really do the kinds of things that we want to do. And the challenge there is that they really focus on how do they provide the kind of the tagging and the data management capabilities that we want. The major libraries outside of audios were really designed in the 90s, and that was before the multi-core era, and because of that, they're really focused on assuming that you have a relatively simple per node kind of setup and a relatively small data volume. When you get to the kind of configurations that we have today, things are so much more complicated that, and the data sizes are so much larger that the techniques that were used then end up not being able to scale as well as we have. IDEOS was a project that Scott and I started, or Scott started and then I joined a couple of years later, that was looking at how those kinds of approaches were being done and then trying to do them differently. So for example, with NetCDF and HDF5, they do a physical linearization of a 3D array. So they just decide what your array dimension orders are, X, Y, and Z, and then they just linearize it, and then that's what they write out in one big contiguous chunk. And so with AUDIOS, what we did is we split that into what data does a single process have. Let's store that chunk independently and just annotate it with how it fits into the global space. And that ended up giving us much better write performance because we didn't have to reorder data that was spread out across the machine. And in almost all cases, it also gave us better read performance because we got more data that we want. No matter how we sliced the data set to be able to do reads, we could actually get to more data per read than we could if we were in this single linearization. So one of the capabilities that all of these systems offer is something they call attributes. And the attributes can be useful in that they can do things like give you what units a particular field is measured in, or they can give you some additional naming information, or maybe an observation time or something like that. But they're limited to the granularity of either the variable or, in some cases, like the group level. And because of that, we don't have the ability to get into the data itself and then tag individual components. And while that's helpful, it's not necessarily enough for us to be able to do the kinds of advanced operations that we would really like to do. And so really the kind of thing we want to look at is what kinds of advanced metadata could we look at. And if we look at the section in the middle here, this is really what we want to be able to look at is we want to look at this metadata that could either be this IO library attribute, or it could be the entire variable, or we want to attach something to say, this range of time steps represents a rapid growth in a particular value. So we want to be able to say, this is an important region temporally that we want to look at. And these kinds of things are just not supported in the existing system. So these are the kinds of things that motivate the work that we're doing. The way that we started thinking about this as we were planning the project was to look at really how the existing tools work and what characterizes each of them. And what we came up with was really that there have been 3 major generations of these tools. The key thing to remember here is that each of these generations was not made obsolete by the next generation. It's more a matter of each generation just represents we need tools to work like this, and then the next generation said, let's look at a different thing that's an add-on capability. So the generations are not a matter of obsolescence, it's more a matter of a shift in what kind of functionality that they're providing. First generation tools are really simple. POSIX, the file system, has the extended attributes. The challenge there is that it's not defined exactly how big those are going to be, and you have to have special commands in order to be able to make sure that those get preserved. So there's something that you could put in, but actually managing them correctly and efficiently is not always easy, and at the same time, the amount of space that you can use varies based on which file system you use. HPSS is the tape archiving system that is commonly used on supercomputers, and it also can store these POSIX extended attributes, but one of the things that it kind of adds is it takes the entire directory structure that you have, puts that into a database, and then lets you tag things in there so that you can be able to find things a lot more quickly without having to go through and look at tape after tape after tape. Starfish is a tool that's a commercial offering, and this actually does, for what most people need, like 80% of the functionality that they want. They say, I just want to know what file something's in. And for this, they go through and they say, you can put a tag on a file that says whatever you want it to say, and then you can search based off of those tags. And for most people, just at a really basic level, this kind of thing works well, which is why it's made into a commercial tool, and we didn't have to try to figure out how to deploy this from a research perspective. There's actually enough commercial interest, and it's something that's general enough that somebody can make a business out of it. The second one I have here is this archive and metadata orderer for the Joint Genome Institute. And this is really a domain-specific tool, which is why it's not really something that would be more advanced. And it works extremely well for the kinds of genomic tagging that people want to do, but it's not really useful for any other particular purpose. And because of that, it's really a very specialized tool rather than something general like we're looking for. In terms of second generation tools, our goal here is, instead of saying what does the file contain, we want to be able to find particular data values within the data. So that's really the shift from the file to the data itself. And the FastFit is something that came out of Mark's Berkeley lab in the US. And the goal there was to use a bitmap index, and you look at ranges of values, and you would just put a 1 or a 0 for a particular data set if a value in that range existed. And then you could look at that bitmap index and determine whether or not you cared about reading that data or not. And it's relatively simple, but at the same time, if you need to know, do I have values in a particular range, it actually works really well. Another one that also is fairly common that many people may know about, and that's SciDB. This really came out of the astronomy community, and that is really taking a 2D array and giving you the ability to mark things like this is a galaxy, or this is a star of a particular type, and those kinds of things, and do that kind of tagging on individual pieces in there. The nice part is that they put in a SQL front end, and that's something that many people were comfortable with. But again, it really is optimized towards the 2D kind of data sets. In terms of the standard libraries that were mentioned earlier, I put all of those in as a second generation tool as well because of the way to detach attributes to particular items in the hierarchy as opposed to subsets of the variables themselves. And that's just looking at some of the pieces there. Something of note, if you look at the audio on the bottom, is that instead of actually putting things within the hierarchy in different places, audio separated it all out into a separate index, and because of that, it can be much faster searching. And that was one of the things that we looked at and said, yeah, this is something that is useful because looking for those attributes to find the kinds of things we were interested in was really the purpose of the attributes in the first place. The third generation tools got much more complex. The purpose for them was to be able to tag things within the data set. So like this is a region where a storm is. This is a place where the gradient indicated that we have a particular value. And those end up looking at how do we put things within the variable itself rather than saying it's the entire variable. The different ways these ended up being implemented were either in the file system, in the key value store, or in a relational database. And each of those had different benefits and trade-offs to them. So Meta, which came out of Lawrence Berkeley, that one is a key value store based version. The challenge there that when we were looking at these kinds of tools was that the key itself ended up having to be really a compound multi-component object. And because of that, when you're trying to search, you have to take each key, parse down into the pieces that you cared about, and then kind of do range checks on them to be able to figure out if it's the right value or not. And those kinds of searching, if they're not exact matches, are very slow. That was one of the reasons why you'd be avoided. Taggit came out of Oak Ridge. This was one that was saying, let's take these kind of capabilities and build them into the file system itself. And while that's a really nice idea, once you try to move your data off of that file system, you lose all that capability. So that's really kind of a trade-off there. One that seems like a special purpose tool, but I kind of include in the third generation, is this biomedical image metadata manager. And the reason why is that it's an image tagger. And it doesn't really care what kind of image it is. It was really developed for the biomedical research areas. It's just that you could basically put anything in there. So unintentionally, they made something that was really general purpose. The last one is Empress, and that is the one that came out of Sandia that was with me and one of my students as part of a joint project with Scott and others. And that was, we looked at using a relational database because of the indexing capabilities allowed us to search really fast. So we could have a lot of tags and still be able to find which ones we were interested in and still do range queries on them and have the database engine handle all that matching. And since it already has all the optimizations for doing that kind of matching built in, we didn't have to try to make it better than what the database community has already done. So I will skip this time here and get on to, here we go. So the fourth generation is really what we're working on now. And the goal here is we want to be able to look at things like these derived quantities, like the combustion. When did the combustion occur? And let me switch to the next slide here. So here's 3 simple examples of what a query might look like logically. So for the first one, we want to look at, for the fluid dynamics run, where is the magnitude of the gradient of a particular variable of a particular size? And that ends up giving us an ability to identify when in the simulation things occur and what region of a particular variable it occurs. That's not something that we actually store directly.
Minimize your Zoom window. Thank you.
Okay. All right. The second one is a particle and cell code. We want to be able to look at where the motion ends up causing a vortex within the material, whatever that we're simulating on, and that's something else that, again, we're not going to be able to see directly, but we want to be able to look at as a derived value. And the last one mentions the combustion. So the system that we are developing, we're really at the start of the second year of a 3-year project at this point, really has this kind of a structure where we're looking at using the Adios engine that is coming out of Oak Ridge, and the goal is that we want to use the query front end and the integration into the analysis tools that Adios has. We want to be able to use the storage management so we can do some more advanced data placement things that Hermes, which comes out of Illinois Institute of Technology. And then the last thing we want to do is use that Empress piece, but expand its capabilities some to be able to do some more advanced metadata management. The key pieces here is that we want to be able to optimize everything based off of an entire session that somebody has doing analysis rather than an individual operation. So based off of, they're going to say, I want to work on this kind of thing, and they'll give an example. They'll give some of their base queries that they're going to start from, and then based off of that, we want to pre-stage data to be able to optimize things. So that starts out fast, and then based on how their session evolves, what actually is going to be stored into the caches will change over time, and then an area we want to incorporate machine learning to do that. And so we had an initial integration demo that we showed at SC a few weeks ago, and beyond that, we have really just a work in progress. But we thought these kinds of ideas were important to be able to move the actual process of generating science out of these kinds of simulations and observations was the right next step to take for us to be able to get our time to insight reduced.
Okay, good afternoon, everyone. So throughout this week, we heard a lot about high-performance computing, about being on the front end and the front edge of generating data, and what that means for organizations like universities and research centers. But a part of that workflow is, and throughout this week that was very clear, is it's difficult then when that data is generated to make sense of what that data is, and more importantly, how do we share that data with other organizations? Hello? We're good? We're good. With other organizations and institutions in a way that is, how do we create this standard platform where we can share this data, add custom metadata, make that metadata searchable and available to everybody? That's the big challenge. So with that in mind, a little introduction about us. We've been in the market for well over 40 years, traditionally building large tape libraries. And these tape libraries are used by large organizations around the world to store large amounts of data. CERN, NASA uses them, CSIR uses them. So originally we've been focused on this traditional hardware, like I call it traditional. And more recently, we've been developing software solutions that allow us to bring that was once seen as a something that sits in the end of the data center that stores data. Nobody knows what it is or exactly what data is in it, and bringing it forward towards the day-to-day operations at the front end of applications. So I'll show you how this workflow works and what we've implemented at CSIR through the guidance of the research. Of course, the project was spearheaded by those fine people there in the left side of the corner. Of course, there were partners involved, but the idea was to present and build this long-term archive solution. And the idea is that we'll integrate eventually different departments. The requirement for this specific platform was to integrate with iRods to store and host research data. This specific solution was spec'd to deliver 20 petabytes of archive capacity, with the idea that we could expand it easily without actually building another data center and expanding that library beyond the frames that we designed. So 3 frames delivering 20 petabytes, easily scalable up to 60 petabytes within the same space. So this, because we wanted to develop and build a solution that not only gave the team at CSIR and all the connected partners the capacity and the ability to store their research and their data in this platform, we went a step further and thought, okay, so once we have the data in, how do we make this available and shareable and searchable to all the other institutions that could benefit from the research that sits here? So we researched further, and one of the challenges we saw, especially in the HPC environment, was that data was created, some experiments and researchers didn't even finish, but they still stayed on the HPC cluster. They still took space and valuable resources. So to mitigate that, we started working with the team to implement what we call the Veil node. And the Veil node is the structure that looks effectively at the data that comes in. We can catalog it, we can harness the existing metadata on those files and those projects, but more importantly, we can add custom metadata to it. So the student or the researcher at point of archive can really catalog and append metadata to those files. This is important because not only that researcher or that department knows exactly what data we're archiving, but it also opens up that research, of course, given the permissions, to other institutions or organizations. Not only can we do that from a purely in the education field, if we want to share the data and the research, but we can also monetize it at some point because some other institutions might be interested in this data. So this data is already cataloged. There is a way that we can share through the Veil node this data with any organization around the world without opening up our data or our network to them. So the way we do that will become clear, hopefully, through this presentation. This is a snapshot of the environment, so a 3-frame library with 16 LTO9 tape drives. And this library will continue to be compatible with the LTO structure. You can just remove the drives, upgrade them. The service stays online as it should be. So there's no limitation in terms of the next 10, 20, 50 years because we're protected with the LTO roadmap. Connected to this library is the Veil node, which is effectively represented here by the Black Pro, and the Black Pro is an S3 is presented as an S3 connector that then connects to the iRods environment in Cape Town. So under this infrastructure, we have full visibility of the data. This is a bidirectional communication. And this little node up here on top of the library, this is what we would deploy in any organization within the country or any organization around the world. And by doing that, they become immediately connected to the Veil node. So this becomes this collaborative infrastructure that I can seamlessly, and depending on the permissions, share whatever data I want immediately. Let's, for the sake of arguments, imagine that 2 large universities or 2 universities are working on the same project. As soon as I create data here, they become immediately aware of it, and they can access it as if the data was stored locally. So that's how powerful this collaboration tool is, and how we aim to eliminate the silos in what is, traditionally a bit of a challenge in sharing this data, catalog it, and make sure that we understand the full provenance of data from creation, or the research, that I should say, from creation up to a finalized project. So we can connect to any source. This is bringing it back a little bit. Any source, and those sources can be HPC environments. They can be lossy file systems, GPFS, local shares, POSIX file systems, CIFS, SMB. You get the idea. Anything that is considered storage, even a network share on my laptop, is a candidate to be connected to this infrastructure. Once we do that, we have several tools that will effectively parse through that data, catalog it, like I said, harness the metadata of those files, and we can, once we have that information on our side, we can immediately have a clear view of what that data is. So imagine on really expensive HPC environments or really expensive fast storage, flash-based, for instance, I can immediately create a policy that moves that data to a more effective storage tier. So I can say, okay, let's look at data that hasn't been touched in 3 years or more. Immediately, because I already did the work of parsing through the file system, our tools already have that information, I can immediately move those files to a more appropriate tier. But here's the kicker. The challenge in doing that, there's nothing special in doing that, but how do we do that without orphaning users and applications of accessing that data? From a user and application perspective, these tools are intelligent enough to leave the data from a hierarchical perspective exactly as it is today. So even though we've moved that to a new location, me as a user, as a student, a researcher, when I log into my session, everything looks exactly the same, but now that file is sitting somewhere else. So hopefully by now you understand purely from an operational perspective how valuable this is. On top of that, there's the collaboration piece. So these engines have high availability models built into them, load balancers. Everything is managed from this perspective, leveraging the existing performance from your compute nodes, from your network, so there's no latency introduced by this process. Once all that data is cataloged, I've identified the policy I want to run. I can send it to native S3 targets. I can send it to on-prem Glacier, which is the environment that CSIR has. So this is effectively exactly the same thing as sending it to the cloud, but it's on-prem. In fact, we use the same SDK as AWS, so it looks and feels exactly like AWS Glacier does. And this is the platform that CSIR has today. We can send it to on-prem storage. We can send it directly to tape as well. And now with Veil, once the data is sent to this layer, and for all elements that belong to the Veil node, as I mentioned, you just need to deploy a node. There's no storage in that node, so it's just connected, if you will, to the environment. Then I can share this anywhere. I can use the services from every cloud manufacturer in the world and have those services processing running on my local storage. So I don't have to upload my data to the cloud. I don't have to worry about ingress and egress fees. I own the entire ecosystem, and this infrastructure allows me to share data how I want, with who I want, and allow my institution and my students to search for the files that effectively they need. So hopefully now you can understand that what this system does and what CSIR now has is a platform that allows any organization around the world and in this fine country to not only archive the data, but share in a way that is collaborative, that can be monetized, of course, in a way that is secure and open to everyone. So as long as the policies are defined and we identify those data sets, in the University of Limpopo, I can share the metadata and the research that is done here and just cherry pick the data that I want. So we're effectively not only helping clean the data, helping clean those fast primary storage and HPC clusters that we've heard this week a lot about, but I can create this workflow after that data is created, after the research is done, and open this research from a collaborative approach once again. So that means that any storage that is sitting underneath the Veil node, and that storage can be direct attached, like I mentioned, any NAS, on-prem Glacier, S3, HPC environments, Any S3 compatible application can connect with, and we can present what is traditionally a SIFS or an NFS target as S3 or vice versa. We can effectively look at data, create a clear view. We can integrate with other applications. All of it is non-proprietary. It uses API and scripting. So if you already have the tools in house, you can easily connect to this environment and build on these tools without any additional charge or any additional licensing. So a quick slide just to highlight the differences between an Amazon S3 and a Black Pearl S3. There are currently 4 tiers in Amazon Glacier tiers. This is the implementation that we have now at CSIR. So as hopefully you'll see, all the benefits that you have from those expensive cloud offerings, which of course become impractical to use at the scale of data that we're generating. But all of those benefits exist here in-house today. So you can benefit from all of those features, instant retrievals, large archive, long-term archives, up to the exabyte level, hopefully. So you get all the benefits, and it looks and feels exactly like AWS does, like I mentioned. Another important aspect is the total cost of ownership of these solutions. And by these solutions, I mean a combination between disk or flash and tape behind, versus the same solution on a pure disk or flash deployment. It's named here Rep X, but I haven't seen them here today, so I'm just going to say it's probably, I might be recorded, Nutanix. So for the same capacity, it's easy to see how much more effective from an energy consumption or a total cost of ownership, both in CapEx and OpEx, a solution like this is. And the reason for that is, of course, in terms of energy consumption, in terms of maintenance, in terms of the end of life cycle of these products, right? Until maybe 5-7 years on a disk solution, the tape will last for as many years as you want. So it's designed to be kept for many years, well past the 7-year threshold of what a similar disk solution would take. Another very important aspect, of course, and we heard all about accelerators this weekend and GPUs and CPUs and the power that those technologies consume. When we look at power and cooling, it's even more dramatic, the difference between solutions, traditional disk-based solutions and now flash-based solutions, and take purely from an archive perspective, of course. You won't run any calculations on these units, of course. But again, it's something that is very important to highlight, because yesterday in one of the talks, to cool these GPUs and these accelerators now, we're looking at direct cooling. So it's going to become a big issue in terms of power consumption in the future, and this is our approach to help mitigate that challenge, is ever increasing and ever focusing on more environmentally friendly solutions. And I don't think we'll ever be net zero, but we're very close to it, especially comparing with those like-for-like solutions. So there are benefits between object-based and object-based tape. Again, this is complementing the previous slides. I'll just skip this, just highlighting how much more effective and cost-effective those solutions are versus the traditional-based disk. So there are 2 options and 2 solutions that we have similar to this one. The first one is with the cloud-based node, and this is just a server as a service that we run in the cloud that is configured by us. There's no data exchange between the source and the service. It's there purely to synchronize the metadata across the nodes that belong to the Veil node. It's encrypted data. There's no relation between that metadata and the data that sits on-prem or that we're managing. It's purely just to keep everybody safe and everybody under the Veil node to know that if data is created here, if the policy is configured that way, and a university in Sydney becomes immediately aware of it, and vice versa. But we also have on-prem solutions, and the solution that we have deployed at CSIR that we help configure can also be configured like this. The limitation is, of course, everything that you've seen now, you benefit from those features, except this sharing and collaborative approach. So there are those 2 differences, those 2 layers, but both of them are possible if you want to have this environment, but not from a collaborative approach, benefit from all of these features but keep things locked in-house. Maybe the nature of the data that you're using or that we're storing in this environment is not a candidate to be shared for whatever reason. Those environments are also available. This entire infrastructure scales in 4 dimensions. In object count, of course, we're virtually limitless in terms of how many objects, billions of objects we can manage. We haven't reached a limit yet, and we're still trying to find and generate data to test that limitation. Of course, in terms of the capacity, we can scale on the hardware level, to the exabyte. Large numbers of exabytes. We have the largest library deployed in the world. It's a 44-frame library, delivering well over 1 exabyte. In terms of the performance expansion, the more disk nodes you add, of course, you're expanding capacity that way. You're also expanding the performance that way, and you actually improving the performance of how these nodes talk to each other as well. So the more nodes, as we've seen this week, this is now no different. The more nodes we have to the environment, the better performant the environment will be. And of course, multi-node bucket expansion is important because I can create this not only from a one-to-many or one-to-one environments where, for example, there's a bucket here where I'm working on some data and I want this data shared with 2 other universities. I can create this collaborative landings on this bucket where everybody is collaborating within the same environment and the same bucket. So that data, that becomes a source of truth, if you will, that then we can immediately replicate to another bucket. As data is created, it can't be tampered with, we can lock it. There's bucket locking and object locking available in all of these units without any additional license. 4 different workflows. The applications on top, talking to an S3 client or an S3 Glacier client, offloading to the S3 Glacier. The second example, synchronized buckets duplicate to on-prem Glacier. So the example I was giving earlier of these buckets being pre-configured with a policy, as soon as data lands, gets immediately copied to somewhere, another department or another region. We have the option to have S3 to local storage. Of course, that S3 layer there can be, I'm referring it to S3 from this Glacier perspective, but it can be the iOS system, it can be any HPC application, any file system really. Copying to S3 and S3 Glacier, and of course purely from a backup long-term retention perspective, I can send that directly to this S3, and this S3 can be hosted anywhere, and send data and archive it to this layer. All of this is cataloged. All the data that is archived is, like I mentioned, we can add metadata, we can harness the existing metadata and create policies around the data using those metadata tags. And that's it. Thank you. Any questions?
All right, thanks, Miguel, for your interesting presentation. I think mine is just 2 bits. One is for clarification, and the other one is just a remark on what would be the strength of each of those. You mentioned 2 control options, and you made a comment about a limitation on the collaborative approach. I'm not sure if I understood that. If you could just clarify what you meant by that limitation, and also given those 2 approaches, what would you say is the strength of each?
There's no way for me to share that data with anybody else. I can still share data, but I would need other applications, other network configurations outside of this environment. So there's the added effort of selecting that data, dumping that data, or putting that data somewhere else, and then sharing it from that layer, if that makes sense. This is with the on-prem only solution. So imagine, for instance, we have use cases of companies that use this technology, for instance, in the automobile research, driverless cars, and all of the research that is done on that field. That information, for obvious reasons, for commercial reasons, they can't share that with anyone else. Nor are we allowed to put this connected to the cloud, even though it's highly secure. In terms of SLAs with the governments themselves and these companies, they're not allowed to have this connectivity outside of the data center. but they still need all the benefits that we talked about, cataloging the metadata, creating these projects, having the ability to look at data regardless of what it is and compiling all of that data. I need data from the wind sensor on this car on this day, you know, and the certain altitude, whatever those variables may be. Through the metadata policy that we have, I can cherry pick and get that information regardless of where it sits. So all the benefits are there, but the cloud, the sphere control element allows me to open up all of this to any organization that belongs to the sphere, the Veil sphere that I've mentioned. So I can put a node in University of Limpopo connected to the CSER environment. You can not only use that to archive your data to their environment, highly secure, you own the bucket, there's no way for anybody to intercept that, that data. But you can also, if you choose to do that, open that data to any university in the world that, again, belongs to this environment. And that is only possible through the cloud service that I mentioned earlier. That will be the main difference between them and the benefits of one over the other.